So it is for me a great pleasure to meet you, even if alas just virtually. It was more fun when these masterclasses were done in person. And this is the second engineering masterclass of the day. I attended most of David's talk this morning. And I will warn you that quite intentionally, this masterclass is going to be about something completely different from robotics or the sort of things that David was talking about this morning. And I said quite intentionally, because I think it is one of the ideas of the engineering fellows at Corpus, to be able to give prospective students an idea of how wide the heart of engineering can be. So how different the different things that an engineer can look after. Myself, I am a professor of infrastructure geotechnics in the Department of Engineering, and a significant proportion of my more applied research has dealt with urban tunneling, so creating underground space for different reasons, but mostly for transport reasons. And today I would like to tell you something about the challenges of creating underground space in historic cities. And I will use the example of the third line of Roma Underground, line C of Roma Underground, and I will try to illustrate very briefly the approaches that were taken to evaluate and minimize the impact of tunneling on the built environment, that in the case of central Roma is historical, archaeological, monumental, and artistic value. So why is this not turning? Yes. So let's start from the project. So an overview of the project. Once completed, line C of Roma Underground will run from, can you see my mouse, by the way, or shall I make it, can you see an arrow?
I can see your mouse.
Okay, perfect. So once completed, line C of Roma Underground will run northwest to southeast of the city center and reach out to the eastern suburbs of Roma for a total length of more than 25 kilometers and 30 stations. The tender for detailed design and construction of the line was awarded in February 2006, that is about 16 years ago, just more than 16 years ago, for a total value of about 3 billion euros. And these 3 billion euros have escalated during the years to reach about 4 billion euros, making line C of Roma Underground the single most important civil engineering project under construction in Italy at the time. As indicated in this slide, the line is divided into 7 contracts. And the stretch between Montecompatri Pantano at the beginning of the line and Giardinetti is runs overground, whereas from Giardinetti to the end of the line is being excavated using the 2 EPB shields with a diameter of 6.7 meters. The part of the line between Montecompatri Pantano and Lodi was relatively straightforward to build, was open to the public and fully operating by 2015, that is about 8 years after the beginning of construction in 2007. It then took another 2 years just to open San Giovanni stations in March 2017, and construction of contract T3 is now coming to an end with the Ambaradam and 4 Imperiali stations expected to open towards the end of this year, so end of 2022. And in the slide, just to give you a progress on the works, this is the speaker. This guy is as a ground engineer, is assigned a site ground engineer that is checking the progress of the station tunnels at 4 Imperiali station. So this is all very recent, but really coming together. Now, if we go back to the timeline that I've just told you, I'm sure that it has not escaped your attention that in the last 5 years, the rate of advance of the line has reduced from more than 2 stations a year to about half a station a year. So 1 station every 2 years. That is about 1/4 of the original speed. And I really hope that by the end of this lecture, you will have a clearer idea of why this may be the case. Now, this is an aerial view of the historical center of the city of Roma with an indication of the central part of the route, that is this green line going through the historical center. And this consists of about 5 kilometers of twin running tunnels and 6 stations, namely San Giovanni station, where there is an exchange with the existing line A of Roma Underground, Ambaradam Ipponio, 4 Imperiali station, where there is another exchange with line B and station Colosseo, Venezia, Chiesa Nuova, and San Pietro. Now, this old photographs shows one of the tunnels of line B of Rome underground, as it was boldly constructed by cut and cover. That means that you create a trench and then you build a tunnel inside the trench, right next to the Colosseum. You might have recognized the Colosseum. And this serves us as a reminder, right at the beginning of this lecture, of what was deemed acceptable in the 30s, and is definitely not anymore. And what I'm saying is that this type of construction, so close to archaeology and built environment, is nowadays not considered acceptable. The concrete for the tunnels of line B of Rome underground is cast against the Roman concrete of the foundation of the Colosseum. So this is definitely not something that we would do anymore, and possibly motivates the sort of studies I will be talking about. So let's go back to the central stretch of line C. This central stretch of the line falls in part under contract T3, which ends at Piazza Venezia, where there is this yellow line here, and in part under contract T2, from Venezia to San Pietro. And these two contracts could not be more different, both from the point of view of the built environment and from the point of view of subsoil conditions. So contract T3 is also called the archaeological contract, as the buildings potentially affected by the construction of the line are essentially all monuments of Roman age. Right at the beginning of the contract, so here we're very close to San Giovanni station here, there are two of the main gates of the ancient Aurelian walls that are Porta Sinaria and Porta Metronia, both from the 3rd century. As you move a little further down the line, here in this red circle, you find the Church of Santo Stefano Rotondo, which is from the 5th century, and then the Amphitheatro Flavio, the Colosseum, from the 1st century, and a little further up, the Basilica di Massenzio, this here at the bottom left of the slide, and the Via dei Fori Imperiali, that where you have the Fori, the Roman Fori on either side of the road, and ends in Piazza Venezia. Once you arrive in Piazza Venezia, sorry, let's go back. The contract T2 starts from Piazza Venezia, from here. This is contract T2 going to the river, the Tiber River. And we are in a completely different built environment, because we are now in Renaissance Roma, where we have a very, very great density of historical masonry buildings, all potentially affected by construction of the line. And of course, there are far too many buildings to be able to mention them all, but just to take you a little bit along the line, as if we're taking some touristic tour through Renaissance Roma, in Piazza Venezia, we find the last Roman monument potentially affected by the line, that is the Colonna Traiana from the 2nd century. And then the Church of Santa Maria di Loreto, which is very, from the 16th century, very representative of the general built environment along the stretch of the line, but also things such as the Vittoriano, that is a kind of a monster, very clumsy building, which was built at the end of 1800 from the new King Savoia coming to Rome and making Rome their capital. And the Romans call it the typewriter, because it looks like an old Remington typewriter machine. And as you continue, again in Piazza Venezia, you have Palazzo Venezia and Palazzo Grazioli. Move along the Church of Sant'Andrea della Valle and Palazzo Massimo alle Colonne, or the Oratorio dei Filippini and the Church of Santa Maria in Vallicella, the Palazzo della Cancelleria, the Palazzo del Banco di Santo Spirito. This is the Antica Zecca. This means the old mint. This is where money was printed in the 16th century. And the Palazzo Sforza Cesarini. And this way we've reached more or less the river. Now, this slide shows the soil profile and groundwater conditions along contract T3, that is the archaeological contract. And if you look at the soil profile, this has a base layer of stiff over-consolidated clay of Pliocene age that is called the Monte Vaticano clay, overlain by a layer of sand and gravel, that is this yellow layer here of about 10 meters thickness, and this is from the Pleistocene. Above the sand and gravel, you get a variety of deposits that are sandy silts or clay silts that belong to the Paleotevere. Paleotevere means the ancient Tiber. That means that these were deposited essentially by the flow of the river Tiber. And then you get some made ground. You know, if we forgive some of the details like the pyroclastic deposits in this area or the more sandy Valle Giulia deposits, essentially you have the stiff clay and sand and gravels that creates the base layer of all the subsoils, and then a variety of silty sand, silty clay, silty sands. And as you can see, the Pleistocene deposits have these kind of ditches, these little valleys that are cut into the Pleistocene deposits, and they correspond to little brooks or little rivers that were running into the main Tiber River, and they were cutting through the Pleistocene deposits. Now, the final layer of the soil profile is this layer of made ground. And made ground in central Roma means archaeology. So it is forbidden ground. And in order to avoid direct interferences with the archaeology, you can see that the running tunnels were placed almost everywhere at depths of more than 20 meters, so that you can avoid the archaeological layers. But this means that you run into coarse-grained deposits, so sands and gravels, and you are well below the groundwater table, which might create some problems from the point of view of tunneling. When you arrive at Piazza Venezia, the soil profile changes completely. First of all, you have this kind of discontinuity, this sharp discontinuity. This is a fault, a geological fault, that brings the roof of the stiff clay, of the Monte Vaticano clay, at the depth of more than 60 meters below ground level. So this is really very, very deep. You still have the layers of sand and gravels from the Pleistocene, like you had in the other contract. But then everything above the sands and gravels is this kind of alluvial deposits of the Tiber River, which can be more silty or more sandy. So the fine-grained deposits, the clay and the silt are shown in green and gray, whereas the more sandy deposits, the more coarse-grained deposits, are shown in brown and orange. So you have a mixture of essentially clay at the beginning of the line, then you go through a bit where you have both sands and clay, and then you get to the Tiber River. And the tunnels are deeper in this part of the line. They go of depths of about 30 to 40 meters and getting deeper towards the river. The groundwater table, of course, is connected to the level of the water in the Tiber River, and it is more or less at the contact between the made ground and the geological soil profile. So it is where, you know, the made ground corresponds to the bottom of the archaeological remnants, because the Romans were not very good at building underwater. So they would found everything more or less where you get the current position of the groundwater table. Now, what are the main design issues for a project like this one, for the central stretch of Line C? And these 4 design issues are listed in this slide. Essentially, you have to predict the displacements induced by tunneling, assess the risk of damage to the existing structures, avoid direct interferences with the archaeology, with the archaeological layers, and where and if necessary, design and implement protective and mitigating measures to safeguard the built environment. Now, the first 2 items, these items of predicting displacements and assessing the risk of damage, need to be tackled with a detailed study of the interaction between the construction of the line and the existing built environment, whereas the other 2, the fact that you have to avoid archaeology and you have to protect and mitigate for potential damage, impose significant restraints on the layout of the line and on your construction processes. So let's start from the interaction studies. And I thought that this might be of interest to prospective engineering students, even if this is more from the point of view of the management. And this is a way to explain the context in which these interaction studies were carried out. So this is a flowchart that summarizes the organization that was set up to examine this problem of the interaction of the line with the built environment. So the grantor of the project, which is the municipality of Roma through Roma Metropolitane Limited, required that the general contractor, that is Metro C SCPA, appointed a multidisciplinary steering technical committee to address and coordinate the activities of 5 working groups that were building features and history, geology, geotechnical engineering, structural engineering, and geomatics. And as you can see, geotechnical engineering, I am a geotechnical engineer, so not by chance I put geotechnical engineering right in the middle of the slide. But what I'm saying, it is that geotechnical engineering had to interact with all the other groups, because this is a typical, very multidisciplinary effort that you have to put together. So the way the interaction studies were carried out meant that we followed levels of increasing complexity. So at the first stage that we call level 1, simplified analysis were carried out, in which the ground movements induced by tunneling were computed using essentially semi-empirical formulas. So these semi-empirical formulas are a way to condensate all the experience we have on previous engineering projects of tunnelings, and then you have formulas that will tell you what the displacements and ground surface will be. So you compute these displacements that are computed in greenfield conditions, that is assuming that the buildings can deform following the ground. And then you make a first judgment of what's going on. And then at a more complicated level, at the second level, you want to really run interaction analysis, in which the interaction between the tunnels and the historical buildings is studied using plane strain or 3-dimensional numerical analysis, finite element analysis, in which the building characteristics are introduced. So the weight of the building, the stiffness of the building are introduced using equivalent solids that are fully embedded into the soil. And we will come back to this. Now, at the level 1, at the first level of analysis, the geotechnical group would compute the displacement field induced by tunneling, assuming greenfield conditions and using semi-empirical procedures. These displacements were applied by the structural engineering group. So there are these 2 groups, geotechnical engineering and structural engineering, that are interacting with one another. So the field of displacements computed from simplified procedures by the geotechnical engineers was given to the structural engineers that would run 2D or 3D finite element models of the buildings. And then both groups would make independent evaluations of the risk of damage, and a deliberation was taken. So if the evaluation of the risk of damage was positive, so we were saying, no, this building is not affected by significant risk of being damaged, then we would stop the study of the interaction at level 1. Otherwise, the building was taken to the second level of analysis, in which, first of all, we had to define an equivalent solid, and we will come back to this, to represent the building. And this equivalent solid had to be included into finite element analysis that were run by the geotechnical group of the construction of the line. And a new field of displacements would be computed from interaction studies, so from this finite element analysis in which the building was included. Again, the new field of displacement would be passed on to the structural engineers that would run a 2D or 3D finite element analysis, and then there would be a damage reevaluation. If the deliberation was positive, then the study would stop here. If there was still significant risk of damage, then remedial and protective measures had to be designed to protect this particular building or this particular monument from construction of the line. Okay, so this is a plan view of contract T2 from Piazza Venezia, that is about here, Piazza Venezia, to the Tiber River, about here. And the shaded areas, all these areas that you see with a shade, either in yellowish or light bluish, baby blue, are buildings for which the superintendents required for detailed interaction studies. So the yellow ones are the ones that passed level 1 analysis. So we stopped the study at level 1, whereas all the blue ones were examples where we had to carry out finite element analysis, and we had to account explicitly for the interaction between the building and the line. Now, the entire line was divided in 3 zones, Zone A, Zone B, and Zone C, that are different from the point of view of the subsoil conditions. In particular, this Zone A is where the soil profile is very simple. It's essentially made of normally of a soft clay. So there are about 60 meters of soft clays, and then at the bottom of it, the stiff over-consolidated clay and the sand and gravel. And I will use one building, one specific building, that is Palazzo Grazioli, that is the chap in the circle, to detail the procedures that I have just outlined very briefly. The reason to choose Palazzo Grazioli is that Palazzo Grazioli is a very regular masonry building, so it's a very simple building, small. It has an inner courtyard and it has 4 facades, 2 of which are more or less parallel to the tunnel axis and 2 of which are more or less orthogonal to the tunnel axis. The building has 1 basement floor, and the depth of the foundation is about 9 meters below ground surface. That is more or less at the contact between the made ground and the natural soil, and more or less at the position where the groundwater table is along contract T2. So I said that at level 1, the first thing you do is you work out the displacements on the basis of empirical relations. And essentially, these empirical relations are formulas to compute the profile of displacement at ground surface and at depth. And it is well known that the ground displacements, the vertical displacements induced by tunneling, are very similar in shape to a Gaussian distribution. And there are ways in which you can compute the maximum displacement at the tunnel axis, which increases with increasing depth, and the width of the settlement trough, that is more or less the standard deviation of the Gaussian distribution. And all of this, in particular, the maximum displacement, depends very much on something which is called the volume loss, which is the amount of soil that you excavate in excess of the nominal volume of the tunnel, and depends very much on the construction techniques. So in this case, the most realistic value of the volume loss for the type of tunneling techniques that are adopted in Roma is 0.5%. This means that you are excavating 0.5% more than the nominal volume of the tunnel, but also the worst case scenario of a volume loss that is twice as much was considered in our preliminary evaluation. So you have some empirical relations that are telling you what the displacements are. And we did compute the displacements. Of course, these displacements can be computed for every advancement of the tunnel face. So here you have the 2 tunnels, the north tunnels and the south tunnel. The north tunnels is going in first, and this red dot is telling you where the face of the tunnel is at the moment. And these are isolines of vertical displacements for a volume loss of 0.5%. And as the tunnel is advancing, you are creating these settlements. So first for the north tunnel and then for the south tunnel. And this way you have computed the settlements. These were computed at foundation level, so that is 9 meters below ground surface, for a volume loss of 0.5%. You can see if we take a section through Palazzo Grazioli, so it is this pink section that is more or less orthogonal to the tunnel axis, you can see that there are 2 settlement troughs that are due to the passage of the first tunnel and the second tunnel. And of course, you get some predictions, you obtain certain prediction for a volume loss of 0.5% and twice as many displacements for a volume loss of 1%. So what can we say? For the more realistic value of the volume loss, the maximum settlement under the building is of the order of 7 millimeters. And the 2 settlement troughs from the 2 tunnels are not interacting very much, so there is only a little bit of overlap in between the 2 tunnels. And most of the building is deforming and hogging, so with the concavity upwards, okay? So you have like a saddle shape predicted for the building. So we are assuming that the building will conform to the ground displacements, and this is the ground displacements that we can compute in greenfield conditions. But this is far too simple. With this criteria, the building was still at risk of damage. And so the analyses were taken to level 2. Now, in level 2 analysis, first of all, you have to take into account the actual soil profile and the groundwater regime. You have to do some proper geotechnical characterization, mechanical properties of the soil, and you have to adopt a constitutive soil model. So you have to be able to say something about the mechanics of how the soil will deform. You have to simulate tunnel excavation. So you have to find a way to simulate in finite element analysis in 2D or 3D the process of tunnel excavation. You have to consider long-term effects, so not just the immediate settlements. And you have to include the buildings with their stiffness, weight, and embedded depth of foundation. And again, I chose Palazzo Grazioli because this is a relatively simple case. So as I told you, the soil profile here is particularly simple. You have the stiff clay, the gravel, and then a very, very thick layer, about 46 meters thick layer of silty clay, and then 9 to 10 meters of made ground, which is archaeology. And this blue dashed line here indicates the position of the groundwater table. The tunnels are here, are about 28.5 meters below ground level, and everything is relatively simple. So we have a very clear idea of the soil profile. Here you can see that there are some indications of some cone penetration tests, some various field tests that were done in order to discover what the mechanical properties of the soils were. For the soils, you have to have a constitutive model. Now, this would be far too difficult to go into for an engineering masterclass, but essentially you have to say something about how the material is behaving. Is this elastic? Is this plastic? And in fact, soils are not elastic at all, are very different from elastic. So they always have permanent deformations. Their mechanical behavior depends on the loading path, depends on a number of things. And so you have to have some complicated constitutive model. In this case, we use the constitutive model for soils, which is called the hardening soil. And these constitutive models have a lot of parameters to them. So like for a simple elastic material, you would want the constant of the spring. Okay, so if you say that something is elastic, elastic is defined by one spring constant, that is the stiffness of the spring. If you make this constitutive model richer, you will have a number of different parameters, and you have to determine them through site investigations, because this is another thing that is special about soil, is that you cannot, like for concrete or steel, specify the materials you want. The materials you want, the materials you have are what you have. They've been put there by geology, and so the only way in order to find out their mechanical properties is to run site investigations. That can be done on site, or they can be done on the lab. You can see, I'm not going to go into the details, but this is all mechanical tests to discover the strength and the stiffness of the soils. And you can see that the very, very, very large number of tests was done to characterize the mechanical behavior of these soils. Now, once you've done this, you will have to devise a way to do 2D or 3D simulations of tunnel excavation in finite elements, and you can do this by removing the nodal forces in your finite element mesh, and then activating your lining and trying to obtain something which is similar. So you create a hole in your finite element mesh, you remove the elements that correspond to the soil inside the tunnel, and then you can either impose a field of displacement or remove the nodal forces, then install in the numerical analysis your lining, and then you find a new equilibrium position. And now, without going too much into the details, you can do different ways. You can kind of calibrate the best field of displacements to apply at the tunnel boundary in order to get reasonable predictions. And you can do it in 2D, or you can do it in 3D, in which essentially you are advancing this hole into a 3D finite element mesh by imposing some displacements at the back of the TBM shield, of the tunnel boring machine shield, and activating the lining, the permanent lining of the tunnel as you move along. Now, the technicalities of these are possibly too much for you, and possibly you're not interested. The important thing is that you need to calibrate your models. You need to calibrate these models, and you do this comparing it in greenfield conditions. You would compare this with your Gaussian prediction. That is a way, the Gaussian is essentially what we already know from previous measurements. So you calibrate your models to take into account what you already know from similar cases. Now, I also said you want to think about long-term effects, and this is because when you tunnel, when you create a hole in the ground to put a tunnel, you will obtain some immediate settlement that happen as soon as you tunnel. But then, in the long term, because the tunnel is never perfectly impermeable, you will have that the tunnel is acting as a drain. So you will have some flow of water towards the tunnel, and this corresponds to lowering of the groundwater table, which induces settlements in the long term. Now, you don't have to imagine that there is a lot of water coming to the tunnel. You don't need a lot of water to come to the tunnel because the soil might be relatively little permeable. So for instance, if it's a clay, you will not get a lot of water coming into the tunnel. You will get maybe a drop of water that will dry out with the flow of air due to the trains that go into the tunnel. But what's important is that you will change your distribution of pore water pressure. So the pore water pressure into the soil will be different, and this will create long-term settlements. And the settlements depend on a lot of things. Depends on the initial pore water pressure distribution, on the excess pore water pressure distribution generated by tunneling, on the compressibility of the clay, but more than everything, they depend on the ratio of the permeability of the lining to the permeability of the soil. And in the permeability of the lining and permeability of the soil are two things that you can determine experimentally. So in the case of Line C of Rome underground, we had estimates of permeability of the soil on site obtained with field testing. We had some estimates of the permeability of the tunnel lining, and we ended up with a ratio of the permeability of the soil to permeability of the lining that is a ratio where you should expect important long-term settlements due to tunneling. And in fact, this was confirmed by some finite element analysis that we ran in 2D in different situations from the point of view of stratigraphy. So these effects are only important when you're tunneling in clay. They're not important when you're tunneling in sand. So we were looking at the beginning, at the initial and last part of stretch T2 of the line, where the tunnels are in clay, but there are some layers of coarser materials. And to cut a long story short, for the most credible value of the ratio of the permeability of the lining to the permeability of the soil, you see that the short-term settlements were in the region of 8, 9 to 10 millimeters, but in the long term, due to seepage towards the tunnel, they would become 5 times as much, nearly 5 times as much in Palazzo Altieri, so where you have the very big thickness of clay, and more than twice as much, about 3 times as much in the last stretch of the tunnel. So long-term effects are important, and you have to consider them in your calculations. And the last element, the last ingredient that we need to take into account is the buildings, the presence of the buildings that, as I said, have stiffness, have weight, they have an embedded depth of foundation. Now, why can't we do a finite element analysis of the building as it is? Now, you can see that if you want to model accurately building from the point of view of structures, you have to include a lot of details, the opening, the beams, the this, the that. And this detail is far too much to include in a model that is a model that might have to be several hundred meters long, wide, and maybe 50 to 60 meters deep to simulate tunnel excavation. So it is far too difficult to have a finite element model that has all the detail that is required by a good structural model and the scope that is required by a good geotechnical model. So what we were doing was creating equivalent solids that would have the same geometry in plan as the real building. They would be fully embedded into the soil, and they were assumed to be elastic. And when I say that they were equivalent, it means that the real building and the proxy of the building, this equivalent solid, would react in the same way to the same field of displacement. So the green field displacements were applied to the complete model and the simplified equivalent solid, and you were varying the parameters, so the elasticity, the modulo of elasticity of this elastic solid, to minimize the differences between the node reactions in the two models. In this way, you could then introduce this finite element equivalent solids into the finite element analysis, recompute the field of displacements taking into account interaction, and apply this new field of displacements to the complete model of the structure to evaluate damage. So this is an example of this thing done in 2D for Palazzo Grazioli. So again, it is our example. This is one of the facades of Palazzo Grazioli. There is a structural model of this facade. in which you can see that there are varying thicknesses of the bearing masonry, there are the openings, there are different materials, and this is the equivalent solid. It's a little structural equivalent solid with just a beam which is fully embedded into the mesh. And these are the node reaction under application of the greenfield displacements. Okay, so you've already seen this, this slide. These were the settlement profiles that were computed at foundation level using the greenfield displacement. And now these are the settlements computed with the 2D finite element analysis under the facade of Via Stalli, assuming the same volume loss of 0.5%. You can see that now this is construction of the first tunnel. So you have a settlement that is more or less maximum where the tunnel is going through, but the building is not deforming, it's tilting rigidly because the building, the facade is really rigid. It cannot conform to the greenfield displacements. And then when the second tunnel goes through, you get more or less that the whole of the building is settling without all that hogging that we saw in the greenfield predictions. And in the long term, when you include drainage towards the tunnel, the settlement is increased a lot. It's increased to nearly 2 times as much as in the short term. Now you can do the same exercise in 3D. And again, this is your Palazzo Grazioli here. You see Palazzo Grazioli is this little chap that is sitting in the middle of a lot of these really massive, heavy buildings. So in the end, we had to construct a 3D mesh that contained all these buildings, because all these buildings with their weight and stiffness, they will affect the results of our predictions. And these are the predictions under Palazzo Grazioli. This is not anymore empirical. This is finite element analysis with the advancement of the first tunnel and then the advancement and construction of the second tunnel with a maximum predicted displacement of the order of 9 millimeters under Palazzo Grazioli. And then in the long term, as seepage towards the tunnel is happening. And here is a comparison of greenfield, 2D finite element analysis, 3D finite element analysis. You can see that the shape, this big hogging thing, is really not happening, and the strains in the building are much smaller than predicted by the greenfield conditions. And here you can see our evaluation of the damage in some ISO damage charts. That is what geotechnical engineers do. We will take the tensile strain, the deflection ratio, put in one of these diagrams and decide whether our damage is negligible, slight, a bit more serious, very serious, and so on. But also the structural engineers would look at in more detail at where the damage is. So you see, this is the 3D structural model of Palazzo Grazioli with the field of greenfield displacements imposed to the foundations, and you can see where the damage is. Now, this is not strain, this is stress, but it doesn't matter. As a message, of course, where you have the reds and the browns, it means we are in trouble. There is a very high level of stress. And you can see that if we use the greenfield displacements, we are predicting a lot of damage. If we do interaction analysis, the situation is much better. And in fact, in the long term, even if the settlements are increasing, the damage to the building is decreasing because buildings suffer particularly from differential displacements and settlements, not for absolute displacements. So in the long term, the settlements are larger, but are more uniform, and so there is less damage predicted. Now, really flying through the last 10 minutes of my talk, avoid archaeology. Every city has their own history, and the history of a city determines very much the conditions in the subsoil. So this is a slide showing the underground of London around Victoria Station. And this was put together by Mott MacDonald when they were doing the upgrade of Victoria Station. So you can see that the underground in London is super crowded. So you have piled foundations, existing tunnels, sewers, shafts, inclined passageways, you name it. So when you build a new tunnel in London, first of all, you have to find some space for the tunnel to go through, but also you have to worry about the interaction of this tunnel with this type of built environment that is mostly modern built environment, a lot of deep foundation, existing tunnels, modern. By modern, I mean even Victorian. A lot of the existing tunnels in London are Victorian. This is not the case in Roma. Central Roma doesn't have piled foundations. Most of the buildings are historical buildings with direct shallow foundations. Doesn't have any particularly important underground system already in place, so there are no shafts, there are no inclined passageways, but you get a lot of archaeology. So for instance, in the area of Sannio, via Sannio, very close to San Giovanni Station, preventive archaeological excavations had indicated the presence of marble workshops of Hadrian's age, and they had recovered a lot of beautiful artifacts, such as this head of god Dionysus. And because of this, the design of the line was changed. So the first design of the line I showed you in the first slide, where you had the geological profile, was this one, where the tunnels were deepening after San Giovanni Station, whereas in the revised project, the line goes deep everywhere in the center, because all these areas are full of archaeological remnants. And in fact, when San Giovanni Station was created, there were a large reservoir of imperial age was discovered, with a lot of pipes, amphors, artifacts. So there was a knowledge that this area was a rich area from the point of view of archaeology. Now, this revised project has a number of problems. The first problem is that now the tunnels have to go under the existing San Giovanni Station, and the existing San Giovanni Station is founded on two lines of large diameter piles, and the clearance between the large diameter piles was not enough for the TBM to go through. So what they had to do was to excavate the tunnels under San Giovanni Station in conventional tunneling, that is with, with some conventional mechanical tools. And in order to do so, they protected the existing San Giovanni Station using artificial ground freezing. And in another masterclass I gave a few years ago, I detailed artificial ground freezing. This is a very interesting. So this is the situation. This is the new San Giovanni Station. This is the existing San Giovanni Station. The tunnels have to go under this station, and they were done so in conventional tunneling. So the shields were dismantled in this shaft, taken to this other shaft, where they were launched again to excavate towards the historical center, whereas this stretch of the line was done in conventional tunneling, and particularly under San Giovanni Station with artificial ground freezing. So freezing pipes were inserted through the walls of San Giovanni Station to create a frozen arch around the new tunnels. And then once the ground was frozen, the diaphragm wall was cut, and then excavation was carried out under the protection of freezing. Preliminary lining consisting of sprayed concrete and steel ribs was put in place, then some impermeabilization, some waterproofing, and then the permanent lining. And only after the permanent lining had been created, the piles were cut and the permanent lining was completed. And this artificial ground freezing created a lot of interesting effects, such as, because the water expands when it freezes, the anomalous behavior of water, that below 0 degrees centigrade it increases in volume. You had a lot of heave that was recorded on the base slab of San Giovanni Station. When I say important heave, I mean 50 millimeters. 50 millimeters, if 5 centimeters is quite a lot. So the trains of the existing line A had to be lifted on jacks so that they were not affected by these construction works under them. And these things can be modeled. Then there is this issue, this is more fundamental research, that is the coupled thermo-hydromechanical modeling of artificial ground freezing. Now, from the point of view of archaeology, the most difficult station was Ambaradam. I thought you might have fun looking at this, because here, about 8 meters below ground level, the headworks for the construction of the station exposed first some military barracks from the 2nd century. Again, this is Emperor Hadrian's time, with mosaic floors, wall paintings, a number of things. And then the even more richly decorated lodgings of the commander of this barracks, that is the Centurione. And at this point, when archaeological remnants of this importance are found, out go the geotechnical engineer, in come the archaeologists, and excavation continues with archaeological means, that is literally with toothbrushes. So, you continue to excavate, but you are excavating in an archaeological manner. Now, Ambaradam Eponium was really a never-ending story. This took forever to create this station, because not only there was this level of barracks and the Domus Centurioni found, but also on removal of the floors in the home of the Centurione, yet another older mosaic floor was found under it. It's not quite as beautiful, but this is very important from the point of view, from the documental point of view, because it testified to the relationships between Rome and Byzantium. So it predated the number of things. So it was very important from the historical point of view. And because of the importance of these archaeological findings, the station had to be completely redesigned, and now it houses a museum where all these remnants can be seen, and the station proper where you go through the gates and so on. Now, final little bit about protective and mitigation measures. This is a very wide topic. There is so much. And this can be tackled in a number of ways. For instance, by physical modeling. So you can create a model TBM. This TBM is only 80 centimeters diameter, so 800 millimeters is a small TBM, but it's a real TBM, a real tunnel boring machine, only done in reduced scale. And it advances in a calibration chamber that is a box full of sand in which you can advance things and see what the effects of tunneling are going to be. And you can keep an eye on existing foundations. So these are some foundations that are loaded with jacks to some level of load. And you can look and you can do smart things such as PIV, particle image velocimetry, to look at the displacements of the ground. You can create barriers. That is one of the mitigating measures that can be used on site. And you can accompany physical modeling with numerical modeling. And again, here you can go really wild. You can do conventional finite element analysis, but also Eulerian or move to Lagrangian, or alternate Euclidean Lagrangian, in which you have some phases in which your steady and the TBM is advancing to phases in which you have the soil advancing towards the TBM. And you can do field trials. So in Rome, we did some field trials of our compensation measures, in particular barriers and compensation grouting. Now, just the compensation grouting, this is the Aurelian walls at Porta Metronia, and the tunnels are going under the walls. This is a picture of the walls, and this is the walls as they go, with the two tunnels going under it. And here, the walls are in a bad state of repair, and all the preliminary analysis had indicated that the walls would suffer damage that was not deemed acceptable. So the idea was that of running some compensation grouting. This means that you sink a shaft somewhere in the ground, and then you put some pipes from which you're injecting grout in pressure as the tunnels go past. And we had the field trial in this garden to make sure that we could actually steer a block of concrete and maintain it to where we wanted. And concurrently with tunnel advancement, we then did some compensation grouting under the foundations of the Aurelian walls. Now, needless to say, when we excavated the shaft for doing the compensation grouting, there were more important archaeological remnants that were found in this shaft. So this work again took forever because you needed to set up the shaft. The Aurelian walls were fully instrumented with a lot of modern instrumentation to see the behavior, and the intervention was very successful, whereby the walls didn't move very much at all. Now, I will not talk at all about Santo Stefano Rotondo because I think this would take us forever, and I've seen that I'm running out of time. What I really wanted to say is that when you do a big infrastructural project such as an underground line in an historical city, there are a lot of engineering challenges. And really, these engineering challenges are born out of soil structure interaction that requires analysis with levels of increasing complexity, because you cannot, the buildings are too many, the situations are too many, you cannot create a finite element analysis for every single building. So you have to create reliable models that you can analyze, that you are capable of analyze. And it is important that you do a careful geotechnical characterization and have at least two independent evaluations of damage from the geotechnical point of view and the structural point of view. Archaeology is a problem, but it's also an opportunity. I want to say that nobody was going to carry out archaeological excavations in the center of Rome. So construction of the line provided a lot of knowledge on the ancient city as a byproduct. And of course, it is a problem because it required to modify the design, and to use innovative construction procedures such as artificial ground freezing. There are mitigation measures. I didn't say very much about them. They are a variety and are very site specific. So you need really to look at the problem and have an idea of what you want to do. There is a lot of research that goes with this type of projects. So you can model EPB tunneling with finite element, do physical modeling, advanced numerical modeling. You can model the remedial measures, the construction processes that contains a lot of interesting physics. The physics of water freezing into the ground is super interesting. So it is truly a problem where you have to look at the Clausius-Clapeyron equations of latent heat being released in the ground as the water freezes. It's absolutely super interesting. And I think it is clear that if you want to tackle problems like this, you really need an interdisciplinary approach where you are talking to the historians, the archaeologists, you need to look at geology, you need to talk to the structural engineers, but also there is a lot to be said about geomatics, monitoring, satellite monitoring of the works. So really, there is a world of research that accompanies these big infrastructure projects. There are always opportunities to advance research. And if you have any questions, like this is taken from the Centurione house in Ambaradam.
Hi, Giulia. Thank you very much for that. It's nice, as the historian in the room, it's nice to have something that I could look at. So I enjoyed it. We've got a couple of questions, and if you don't mind answering some.
Yeah, shall I stop sharing?
If that's okay, that'd be great.
Yeah, I'm trying to find how to stop sharing.
I can probably just do it for you.
Yeah, do it for me, please. I would be grateful because I'm not finding my stop.
I've done it.
Thank you.
So when you, do you have to include the possibility of natural disasters in your calculations?
You mean natural disasters like such as earthquake, for instance?
I would guess so, yeah.
Absolutely. This Italy is a very, very seismic country. So of course, all of these buildings were built without any seismic regulations, and most of them are not meant to sustain any significant seismic action, even if they did sustain a lot of seismic actions historically. So some of them partly collapsed and were reconstructed, which adds a level of complexity because it's not, some of these buildings have different parts that were built in different historical times, and in some cases because of collapses and reconstructions. So nowadays, whenever you touch anything, the law in Italy requires that you do some seismic upgrade of the structure. So in some cases, structures that have been sitting there like, untouched, because you're touching them in modern times, or you're affecting them with the construction of the line, you have to address the issue of requalification from the seismic point of view. So in the example I didn't show, the church of Santo Stefano Rotondo, there was quite a lot of structural upgrade of the church, because the church itself is very fragile. So in reality, the tunnels of Rome underground were doing absolutely nothing to the church of Santo Stefano Rotondo, because the church of Santo Stefano Rotondo is on a hill. So the tunnels in that area are really very, very deep. So there is very, very little that reaches Santo Stefano Rotondo. But this is an opportunity. So this is where there was some good cooperation between the superintendents and the general contractor, where they could find, ways to use the opportunity of building the line, also to do the structural upgrades for, you call it natural disaster. That is, in Italy, the natural disaster would be essentially seismic. The tunnels are not very affected by the seismic action. It's not the type of structure that suffers very much from the seismic action. You're more looking at the stations is more vulnerable. So where the tunnels joins the station, because there, if there is any shaking, the way the station shakes and the way the tunnel shakes are very different. And so at the connection, you might get a lot of damage. But the tunnel itself is not something that gets very damaged in general, in case of a seismic event.
Interesting. Well, I mean, so does the tunnel, I'm interested now. So is that because of the shape of the tunnel,
Well,
Why did what? I mean, look, I'm not an engineer, so I won't understand. But what is it about the? Is it because essentially the station is a box?
it's essentially because the tunnel is made of the lining of the tunnel is made in rings. Okay,
Yeah.
so it has a certain shear deformability. So if the displacements are not exact, so you can have actions that are transverse to the tunnel section, and this will tend to ovalize your section. But you know, a circular section is a pretty good section. It would be worse if it were in the shape of a box. And then in the longitudinal direction, you have a certain shear flexibility because of all the joints between the different rings. So the tunnel is something that can actually quite well accommodate the ground movements and displace with the ground movements. But where it joins with the station is this kind of solid box and it won't deform. So there is a kind of mismatch of mechanical impedances between the tunnel and the station. And this is where all the trouble it happens from the point of view of structural damage. It's where you want to force something that is very stiff to move together with something that is relatively flexible, and then it starts cracking and creating problems.
Interesting. Catherine asks, when planning and modeling the tunnels, did you consult historians and archaeologists to try to predict where you would find historic sites?
Absolutely. Not only we consulted historians and archaeologists to try and predict where we would find things, we also did preliminary archaeological samples. So everywhere we were planning to do major works, we had samples, archaeological samples that were done before, and trying to understand. So the problem in Roma is not the if there are going to be any archaeological remnants, because this is a point in the center of Roma. This question is pointless. The answer is yes, there are always archaeological remnants. So you want to understand how important this might be, how relevant this might be. So you know, nobody was expecting to find what we found at Tambaradam e Ponio. That archaeological finding was absolutely unprecedented, and in fact, it had it won a prize. It was deemed the most important finding. I can't remember what. That there's an archaeological prize that goes in the Mediterranean countries, and this was considered very, very important. You must consider that, so this is the deepening of the line. So the line is running everywhere underneath the archaeological layer, because we know there is archaeology everywhere. Still, you have to dig the stations. So there is no way in which you can't possibly have a tunnel without ever coming to surface. Otherwise, this nullifies the important, you know, the purpose of the tunnel. And every time you dig a station, you know you're going to bump into something. In most cases, you can document and even dismantle, because it doesn't matter, because in Roma, a lot of these things have more documental importance than artistic importance. But in some cases, when that's very important, you have to change the layout of your station. So of course we did. And I must say that at the beginning of the project, the relationship between the line, the project, and the archaeological superintendent was pretty tense. So they thought that we were the engineers, the monsters, the people that come to destroy the archaeology. So what were we doing? Whereas over the years, a very relationship of mutual trust developed, whereby we were understanding each other's languages and needs much better. And I think this is really important, that you develop a common shared language with the people that are in charge of different aspects of the same thing. So you as an engineer, develop a sensibility towards what you're doing. Like, you know, it's like saying, if you are, you are an engineer and you go and see the Louvre, and then you look at the Mona Lisa, and you realize that, you know, the painting is in danger of falling to the floor because maybe the nail is a bit shaky, then you take out a big nail and hammer it in the middle of the face of Mona Lisa. Like, you know, now the painting is absolutely safe. It's not going to fall to the floor, but I wouldn't call this a good solution. Like, you know, so you really need to develop an understanding. Or, you know, there are many, many examples in which you as an engineer have to come to terms with the culture, because, and this is And also the archaeologist has to come to terms with your culture, because I believe that what is really culturally important about the historical and archaeological heritage is also the matter value. So the fact that that thing was made in mortar, and that mortar is of Roman age. So you can't simply substitute it with something else. Like in Chicago, there is a reproduction, I think in scale 1:2, of the Tower of Pisa. And it's a perfect reproduction of the Tower of Pisa. It's leaning, only it's made in concrete and was built in the 1900s. Now, nobody goes and visits that reproduction of the Pisa Tower. It's beautiful. It looks exactly the same as the Pisa Tower in Pisa. So it looks the same. This is to say that the value of an archaeological and historic artifact, it's not just aesthetic. There's something more to it. So there is and therefore you need to talk to one another. You need to understand not just the aesthetic value or something, but also I would say the materic value of something. And you need to develop a shared language about this. It's not easy. It's not easy, but I think this is another great opportunity of this type of projects, that you open up a world. So absolutely working always with as interdisciplinary as possible.
So James asks, how tight were the tolerances on the tunnel dimensions?
The tunnel is built using with mechanized tunneling, so using an EPB, an earth pressure balance shield. And the tunnel dimensions are really tight, because this is kind of mechanized process. You do get slight differences in volume loss. Now, the volume loss, I touched very briefly upon it. It's the volume of soil that is excavated in excess of the nominal volume of the tunnel. And one might ask, but why do you excavate more soil that you strictly need to? This is for a number of reasons. For instance, the shield, so this machine that cuts into the soil, is not a straight cylinder, it's conical. So it is wider at the face, and then it reduces towards as you move towards the tail of the shield. And this is because you don't want the shield to get jammed into the soil. So you over excavate a little bit, but then the soil closes around the shield, and this is creating ground movements. Also, if you do not support the face as you are excavating, some material will come towards the face in the longitudinal direction, and you're continuously excavating it. So you're creating another over excavation. And these things really are very difficult to predict how much you will get. The only indication of how much over excavation you're doing, you get from the settlements you measure above ground. And they depend a lot on the specific machine, sometimes even on the experience of the contractor that is actually excavating the tunnel. So a contractor might do better than another using very similar machines. But the tolerances are pretty tight.
So someone asked, do you use crack propagation laws to manage the tunnels over a longer period of time?
No, crack propagation laws, crack propagation is something you might want to look at in the buildings. And the crack propagation, it's funny that you ask, crack propagation is very important for this compensation grouting. So I told you that in some cases you insert these pipes, these perforated pipes, from which you inject grout under pressure. Now, depending on the materials in which you are, you can do what is called compaction grouting. And in this case, you're injecting a relatively viscous mortar that is expanding against the soil, and it's compacting the soil. But in cases where you have the clay, the mortar that you are injecting is actually not very viscous, it's very fluid, and you inject at very high pressures so that you fracture the clay, and the clay fractures more or less horizontally, and then by injecting mortar impression, you kind of jack up the structure. So how far away from the injection point the mortar will propagate, and what sort of fracture pattern you will get is again an extremely difficult problem in mechanics, in which you have to look at Griffith's law for the energy concentration at the tip of the crack. Very, very difficult to predict theoretically and numerically, but very, very relevant in terms of the success of your compensation grouting.
Okay, so then we've got 2 more questions. Is that okay, Giulia? I'm conscious of time. Is that okay?
Absolutely.
Yeah. So how, on a project like the tunneling in Rome, how do you approach problems of sustainability and global warming? So what are the environmental, like, how do you take into account environmental factors or environmental sustainability?
Yeah, as always with all civil engineering projects, the big culprit is concrete. So because of cement, because if cement were a country, it would be the biggest emitter of CO2. So cement in concrete creates a lot of CO2 emissions. So the first way in which you try and minimize your impact is by reducing the amount of concrete you use. In this case, a lot of attention was also placed on where you would have the plants for manufacturing the rings of the permanent lining, because you also have a lot of CO2 emissions that are connected to transporting things around. So every time you have these rings being made someplace, transported through central Roma on vehicles and wheels, so you really want to optimize location, transportation, quantity of concrete. And one other thing that has not been done at all in Roma, and this has been quite a shame, I think, because it could have been done, is that, and maybe it can be implemented at a later stage, or maybe for the following stretches of the line on the other side of the river that are still at the design stage, is to use the tunnels as for ground source heating. Like tunnels, because the temperature of you can use the ground as for heating and cooling purposes. Okay, so you still would need some conversion, but rather than having so the temperature of the ground is pretty stable, below 15 meters below ground levels, so it's not affected by your cyclic variations of winter and summer. So if you put some heat exchangers into the ground, you can use that as an immense reservoir of at constant temperature. So it's like you have a potential for your heat transfer problem that is always like you have like you have the sea for water. You have an immense quantity of heat at constant temperature. So you can use that as your reference point to heat during the winter. So during the winter you can subtract heat from the ground, and during the summer you can pour heat into the ground. So rather than doing it relative to your air temperature, so say that you want to cool or heat a building. During winter, you have to increase the temperature inside the building, and you start from something which is close to 0 outdoors to your desired 20 degrees. During the summer, you want to work against your 30 degrees outdoors. In Rome, more likely 40 degrees outdoors. If you're doing this against the constant level temperature, so that is the ground temperature, you reduce the amount of energy you need to cool and heat during the summer. And moreover, tunnels, because of the passage of trains, are particularly warm. So a lot of that can be used for heating during the winter, and you can create heat distribution systems that are at district level, because the tunnels goes across several districts. So it's not just a single building having ground source heat pumps under their own foundations, but there is a tunnel and you can connect a number of buildings to that. So it's something that maybe can be explored for the future. This is all ways to try and optimize the energy issues and environmental impact of this type of structures. One more thing I want to say is that Roma is paralyzed by traffic, by car traffic, completely paralyzed. So it really needs underground transport, because for sustainability, you really need to move people getting rid of the cars, because this is creating a problem with pollution that is amazing. And it is also another way to protect the monuments. because this air pollution is actually destroying the monuments. And either you put them under a bubble, a plexiglass bubble, or you get rid of the cars. And I think we should really get rid of the cars and move towards electric trains in the underground and make sure that we can enjoy the surface walking around. In Roma, the weather's beautiful, so we can do that.
Yeah. So I'm very conscious of the time, Giulia. I think quite a few of our students.
I'm fine if the students are happy to stay a few more minutes.
Okay. We've got one more question then, and then we must let everyone go.
Okay.
So what is the most expensive? So has an expensive project that you have been involved in ever run into major problems? And if so, what were they and what did you take to fix it?
Not this project. This project, of course, hasn't incurred in any problems. Like, no, I'm joking. In this case, the major problems really was the interferences with the archaeology. But this is besides the point. There have been a lot of projects where there have been very costly problems, and typically on almost all civil engineering projects, the majority of the problems come from poor ground characterization. So lack of geotechnical site investigation. Now I'm saying this, and you might, it is really, I said it again en passant because I don't have the time to say it, but you must consider that as a civil engineer, most of the time you specify your materials. So you say, I want to build a bridge and I want steel of this class with this strength and this characteristics. Whereas, but unless you're building an airplane or something that flies, a balloon, everything that you build will have foundations. So of course, if you build tunnels, you are particularly affected by the ground because you're building entirely into the ground. But even if you're building a building or a bridge, this bridge or this building will have foundations. So it will have to rest on something. And if you do not, and whatever is underground, you don't know unless you've done some proper geotechnical investigation. That is not just to find out what is there, but also to find out what the mechanical characteristics are, what the state of the groundwater table is. And if you don't characterize that properly, you're very likely to incur in problems. So there is a standard sentence in all civil engineering projects that says, this extra 20% of cost relative to tender cost comes from unforeseen ground conditions. And I think that really the question is whether the ground conditions were unforeseen or unforeseeable. And in a lot of cases, they were foreseeable, only nobody bothered, or they decided, because a lot of people think, this is wasted money. What do I really spend this money for? And in some cases, you might get lucky. You don't spend the money and everything goes hunky-dory and you don't have a problem. But in other cases, if you'd spend just a fractionate money more in characterizing properly the ground, you wouldn't have incurred in the problems later.
Great, thank you. Is there anything else you'd like to say to anyone watching, sort of who's thinking about applying for engineering to Cambridge at all, Giulia?
Well, I don't know. I was fascinated by the number of questions that were at Michael's presentation, because of course you seem to have a lot of questions about, are my A levels going to be enough, or what is it I want to study? And for instance, I am maybe on this respect, I'm slightly different from Michael, so I shouldn't be saying this, but because Michael is not here, I will say the same. So he said, like, if you have a fourth subject that is not related to engineering, he's right. If this is impacting on your ability to get really good grades at your maths, physics, further maths, then maybe it's wise to concentrate on the subjects that are more relevant to your topic. But personally, I'm always very impressed when a kid comes to us and is taking A levels and maybe they're doing maths, further maths and physics and Greek literature, or, maths, further maths and physics and Latin, or maths, further maths and physics and music. Because I think that I like that. So it's something I always notice in an application. Of course, each one of us is different. And it's when Michael was talking about the holistic approach, you will be interviewed, but you will have 2 interviews and you will be interviewed by 4 people. So it is obviously 4 people will see different things in you, then they will discuss, they will convince each other about, but for me, it's always a nice sign when I see that the person is not completely one-dimensional, that they have interests outside just, integrals, derivatives, and things like this, which I like immensely, I'm an engineer, but still, there's more to life than just maths and physics.
Well, I mean, again, as a historian, I would agree.